hopefully we've all got it.
Are you recording class?
I am now.
Awesome.
All right. So this is definitely something we'll want to be able to do on the quiz on Wednesday. Is start with an integral, which is over on the board there. Got the piece of area that we're talking about, and we want to write in sigma form the sum of a number of rectangles. In this case, I wanted you to write 10 left rectangles. Okay? So what's the process? Well, you need the width, right? So 5 minus 2 divided by 10, so they're 3/10 wide, 0.3. Anybody use decimals? Okay? I don't care. You can use decimals, fractions, whatever. I typically use fractions. So you got 3/10. Now the thing I told you last week that I often do, I don't care about what this curve is. Doesn't matter when I'm doing this. I don't have to graph the picture if it didn't ask me to. But I like to draw myself an x-axis at least so I can see my subdivision. So I'm going to go from 2 to 5, and I got 3/10 wide, so I'm going to have 2. I'm going to have 2 and 3/10. I'm going to have 2 and 6/10. I'm going to have 2 and 9/10. I'm going to go all the way over to 50/10 or 5. Okay, and then I start writing that down. So my function height, now, again, your left edge has to start at 2. If they're left rectangles, we start at 2. If it was right rectangles, we'd start where?
2 and 3/10.
This one, right? 2 and 3/10. We'd start one width over from our left edge. So if our left edge is 2, the width is 3/10. So the first right rectangle would be evaluated into the function, plugged into the function for x at 2 and 3/10. But they're left rectangles, so we start on the left edge at 2. 2 and 3/10. 2 and 6/10. All the way. Now I didn't fill that in. What should go in this last one? 2 and 27/10. Or, now, did anybody use improper fractions here instead of mixed numbers? Now, actually, to be honest, I almost prefer the improper fractions, but it's totally up to you. So you see I wrote down 20/10, 23/10, 26/10, 29/10, like that. So this would be f of 20/10 if we'd have done it that way, and this would have been 23/10. And let me show you how that would have looked. This would have been 26/10 and so forth. Okay? And then you'd have had 47/10 over here. All right, now, when I want to write this in my F notation, how do I write the inside here? Left ones are always a little bit weird because they're missing this thing always. And that's why right ones are a little simpler. It's one of the reasons I had you do a left here. But you guys were here on Friday. What did we say about left rectangle sigmas? Start them at 0. So if I start them at 0, then that tells me that this is basically 2 plus 0/10 is what that is. And so what I have is 0/10, 3/10, 6/10. How can I generate a 0, a 3, a 6, a 9? 3i. So this is going to be 2 plus 3i over 10. Now if you did it with improper fractions, you need to make a 20, a 23, a 26, a 29. Well, again, anytime you see that you're adding on 3, what did I tell you last week to think of? Repeatedly adding 3 is what? Multiplication. That's multiplication by 3. So right away, if I see 20, 23, 26, 29, I think 3i has to be involved somewhere. And since it starts at 20, it's going to be 20 plus 3i. So if you did it with improper fractions, you would have had 20 plus 3i over 10, like that. So when I is a 0, that would just give you 20 over 10, which is 2. The nice thing about doing this with your left rectangles is if this was a right rectangle, we'd start I at 1. And that would give us 2 and 3/10 is our first one, when I is a 1. And that's where our right rectangles would have started. So just understanding that allows you to adjust your sigma when you know lefts would start at 0, rights would start at 1. That's the best way. Now, again, back to what Brent asked earlier, they don't have to. We could have written this so the left started at 1, and we could have written a formula in here that would have made that work, and that would have been fine. Okay? And if you come up with that, then that's okay. All right, then we take it out of F notation, so we take this and we plug it in for the x. F of something means take that something, plug it in for x. So this will be ln 2 plus 3i over 10, and then times the width of 3/10. And then this went from 1 to 10. Okay? Yes? What did I do wrong? Yes. You have to make sure you catch. We're starting at 0, and I didn't even put my 0 on the bottom. If we're starting here, then this has got to be 0 to 9, if you're going with 10 subdivisions. Thank you. So 0 to 9, and then if we wanted to write some, it would just go 1 to 10. All right? Now we get to number 23, which was a midpoint sum. Oh, before I get to that one, I wanted to talk about this idea of where things start. We talked about with sigmas. We could rewrite that, start it at 1, change that formula there, still generate that same sequence. The same thing is true with integrals. Okay, think about this. Here we have the natural log of x, and I know the people in the video aren't going to just see this, but natural log of x goes from 2 to 5. All right, that's that piece of area. What about this integral right here? Isn't that the same? I mean, here's your natural log graph. It has an asymptote here at the 0. It crosses at 1. So this one is shifted left 2. So that means your asymptote's going to be back here at -2. It's going to cross up here at -1 and go like this. Your area from 0 to 3 is going to be this piece of area right here. Right? It's exactly the same piece of area. So it's exactly the same value. So we could take any integral we wanted, and we could shift those things left and right, and we could write an infinite number of integrals that would be exactly the same value, exactly the same piece of area. Okay? So if we did an antiderivative on this, plugged 5 and 2 and subtracted them, did an antiderivative of this, did a 3 and a 0, subtracted, come out the same. All right? So, important to understand. So what I would, the result of that to me is, let's write them as simple as we can. Now some people think they're simpler if they can always start them at 0. If you always want your integral to start at 0, it means this will be more complicated in here. You have to do some of this. Or some people think simple means always have x inside the function. And then that means those will change, okay? And you'll see that as we get into this. I usually prefer the top option on these, okay, when we're doing that. All right, let's do number 23. So this was 23, and you were supposed to do midpoints. How many? Was it 10? Or there's a couple parts to this one. First one was 10. To do 10. That'll be basically the same. All right, so your first step is to find the width, delta x. So 5 minus 0 divided by 10, which is 1/2. So the width is 1/2. So I want to make myself an x-axis here. I'm going from 0 to 5. So my first one's going to be at 1/2, and then 2/2, and then 3/2, right? And then so forth. So there's my width. 1/2, 2/2, 3/2, 4/2, on and on and on, all the way out to 5. Okay? But these are midpoints. So where's my first midpoint? At 1/4. Where's my next midpoint? It would actually be at 3/4, and the next one at 5/4. And I need to write enough to get my pattern. But notice, from 1/4 to 3/4 is a width of 1/2, 2/4, right? From 1/4 to 3/4, from one midpoint to the next midpoint is your width. It should be the same as your delta x. It should be 1/2, which it is. It's 2/4. So 1/4 to 3/4, and so on. So now when I write this out, okay, my first midpoint height would be at f of 1/4 times 1/2 plus f of 3/4 times 1/2, and we get the pattern. Then it's going to go 5, then it's going to go 7, okay? So I'm going to run out of room, so I'm going to stop. And what's my last one? I always like to put the last one in there because it's not necessary, but it helps you to double check, and you're going to see for something we're going to do today, the last one can be very helpful. What will the last one be? 19/4. It'll be 1/4, half a width short of 5, which is 20/4. So since this is at 20/4 at the far edge, the midpoint will be half a width short, or 19/4. All right, so there's my pattern. Now, a couple of things I want you to notice here on midpoints. This always happens, as long as the fractions are reduced. That this number and this number This one will be double this one. Always happens on a midpoint. Because think about it. How do you take half of a fraction? What's half of a fourth? An eighth. What's half of a tenth? Of 1/10. 1/20, right? You double the bottom number and you take half. Double the bottom number. Makes sense. You multiply by a half, you're multiplying the bottom by 2. So when you double the bottom number, you're taking half. So whenever you see this connection, when you see one of these expanded out, big hint that you have a midpoint. Now the one we just did, notice you got 3/10 and 3/10. There's a match here on these fractions. So whenever you're in fractions, that's another reason I like fractions. When you see that, left and right rectangles, those will always match. Okay? But with midpoints, you'll see this. So it's a big hint. Now, why is that important? Well, when we go backwards, remember our job today, what we're going to be learning today and talking about today is we're going to start with this. We're going to start with a sigma, and we're going to want to write this integral. So looking at it and identifying that it was a left or a right or a midpoint, and how are we going to identify a left? Starts at 0, right? And so that's why I like picking out these little patterns there can help you to understand. Now, do you absolutely have to identify it was a left or a right? No, but it's helpful if you do. Okay, so anyway, so this one's our midpoint. So now we look at our pattern. All right, so midpoints, I usually start at 1, but like Brenna's question originally was, could it start at 0? Yes, it could. I usually like to reserve that for the left rectangles to start at 0. So the rights and the midpoints, I start at 1. So this is going to go 1 to 10. F of something times a half. I notice I always have a 4 on the bottom. The only thing I have to generate is a 1, a 3, a 5, a 7. What's going on? 2i minus 1. Again, notice they're going up by 1, or they're going up by 2s. You go from 1 to 3 to 5 to 7. Anytime you're repeatedly adding 2, you think 2i. Think 2i. But when I is a 1, if I take 2 times 1, I get 2, not 1. So I got to take away 1. It's always 1 less. Put a 2 in there for I. 2 times 2 is 4. 4 minus 1 gives me 3. And so forth. And so start with 2i, since they're going up by 2s, and then adjust it from there. And there you go. And then the last step is to take that out of sigma or out of F notation. And so we're going to plug that into our function. So it's square root of 2i minus 1 over 4, and then times a half. Okay? Any questions about that? Somebody said in the other class in the answer book they always put the width of 1/2 out in front of the sigma. I don't care. It's fine. I like to leave it in there. Height times width, height times width. But as long as you identify that as a width, that's the important thing. Okay? All right. So let's talk about doing this in the other direction. Okay? Because that's the key element we want to do today. Let's start with this one. So imagine, if you will, that all you were given is this. Now, I think once we get the hang of this direction is actually easier. Less work to show. When you have an integral and you have to write the sigma, you have to get the pattern, right? But before you can write a sigma, you got to see a pattern. And the only way to see a pattern is to write it out. The nice thing about this is there's kind of a set steps to follow. Find your width. Find your subintervals. Write it out. Look at the pattern. Write your sigma, and there you go. So you got a nice set of steps, I guess, to find it. Going backwards is a little more, just kind of guess and check, sort of. It's kind of like the difference between derivative and antiderivative. So let's look at this. First thing I would say about is this. Sigma, messy. Sigma, messy. Integral, not messy. We can come up with something better. Clean, neat, tidy, something. Sigma, Messy. Look at it. 3/10, 2 plus 3i10, right? Messy. Integral, not messy. Okay? Neat. Because here's why I tell you this. Here's why I tell you this, because I see this all the time. I see this all the time. When you go from here to here, we don't have to worry about that because we get the 3/10 and all that stuff by the steps we do. We do the width and we write it all out. We see the pattern and we get it. But here's what I'll see. I guarantee I'll still see this from somebody in the quiz. When they write their integral, they'll have a 3/10 out in front. Or when they do their integral, they'll have their integral go from 0 to 9 here. Or instead of ln x, they'll have ln of 2 plus 3x over 10. They'll have this stuff in here, they'll have that in there. No. All the messy stuff is in the sigma, not in the integral. Now, could you have an integral that went from 0 to 9? Could you have an integral that went from 1/10 to 4/10? Yes, but not in these problems. Okay, it's not going to happen. So let's break it down and let's see what's going on here. What's the 3/10? The width. What's that turn into up here? What's the 3/10 turn into up here?
X.
The dx. It's the dx. The width part of this disappears. Because remember, this is the exact area. How wide are the rectangles when you have an infinite number of them? 0. There is no width when you have the exact area under the curve. And that's what the integral is. So the 3/10 here, because remember, what does this sigma represent?
The sum of the rectangles.
How many? 10 of them. This represents 10 left rectangles added together as an approximation to this area. But when we write the integral, we're not talking about 10 rectangles. We're talking about an infinite number of rectangles. There is no width. So the 3/10 turns into dx. Okay, so that's, once we get that part figured out, that makes that easy. Okay, what about this 2 plus 3i over 10, that messy stuff? Well, that's this messy stuff in here. F of 2 means put a 2 in for x. F of 2 3/10 means put a 2 3/10 in for x. So this messy stuff is where the x goes. That's where the x was. So this function is ln x, right? So the messy stuff gone, x in its place. Then the last thing to figure out is goes from where to where. I think the way to do that, to see where it starts, is put a 0 in for I. Put a 0 in for I. We get ln 2. So the first thing we plugged in is 2. Now here's where it's helpful to understand if this sigma is a left or a right or a midpoint. So by seeing the 0 to 9, I think to myself, I'll bet these were left rectangles. Because remember, you're not going to be told that. In this problem, we were told, here's an integral, you write an L10. So we knew they were 10 left rectangles. In this problem, I'm just going to give you this and say, write the integral that this represents. So you look at it and you say, I think those were left rectangles because of that 0 to 9. And so you plug a 0 in for I, you get ln of 2. And so 2 remembers what was plugged in where the x was. Well, what do you do on a left rectangle? You plug in the very first thing is what? The far left edge, right? We got our left edge or right edge. And a left rectangle, the first thing you plug in is the far left edge. So the first thing we're plugging in when I is a 0 is a 2. I'll bet my left edge is 2. Okay? Now what's my right edge? Let's plug in a 9. Now you got two ways you can find this. One way to do it is to plug in a 9. The right edge is where you stop. So let's plug in a 9. 2 and 27/10. Now there's going to be some people put 2 and 27/10 up here. That would be bad. Why? Why is that not a right edge?
Because that's the left.
Because we're doing left rectangles. And left rectangles stop one width short of the right edge.
So you just add.
So add another 3/10 on. So you're at 2, you put a 9 in here, you're at 2 and 27/10, which would actually be what? 4 and 7/10. You're one width or 3/10 short of the right edge. Well, that's at 5, right? Add on 3/10 to 4 and 7/10, you got 5. So it goes 2 to 5. Now, some people don't like that way as well. So there's another way you can find this. That last bit that we just did there. We just figured out it started at 2, right? We got that. I think that's the best way to do that. Plug a 0 in for I. You get 2 First thing plugged in is 2. That's the left edge. Okay, now how do I get the right edge? Well, I would do this. Delta x, our formula is this, right, for delta x. So all I have to do is multiply both sides by n, because what's b minus a? Total width, right? That's my total width. So if I take my width, which in this case was 3/10, and I multiply that by how many rectangles I had, which is 10, what do you get? 3. That tells you your total width is 3. So if you know you start at 2, it's got to end at 5. Total width of 3. So that's another way to get it. Take your width times how many rectangles you have. Now remember, we have 10 rectangles, not 9. When you go from 0 to 9, that means 10. 10 rectangles times our 3/10, that gives me a total width of 3. If I'm starting at 2, then I have to end at 5. So that's the other way you could find that. Okay, let's check that out on our midpoint problem. So how would we have thought this through on our midpoint problem? So we were given this. Right away, the 4 and the 2 tips me off this was a midpoint. Okay? The 1/2 is going to turn into what? The dx. The messy stuff inside the square root, that's where the x was. So the function is going to be square root of x. Oh, wait, by the way. The 2, right, when I put a 0 in for 9, I got ln2, so that's where I started, so that was my left edge. I could have done, some people do the messy stuff as the x here, and then they just look at that. They say, okay, I started with 3/10, then I went to 6/10, okay, so now my integral will start at 0. So some people would have thought of that as doing 2 plus x, and then going from 0 to 3. And those are the people that always want to start this at 0. But to me, it's easier to say, okay, put a 0 in, you get ln2, okay, first thing I plugged in was a 2. That's the left edge. So this integral started at 2. And then that way, that just keeps x in there all the time. And you don't have to mess with like the x plus 2 in there. So that's up to you. Okay, but let's look at this. So we got our dx here. We got the square root of the messy stuff. That messy stuff is the x, so that's square root of x. Now we plug a 1 in. We get 2 minus 1 is a 4th. So the first thing that got plugged in for the x is a 4th. The width is a 1/2. Oh yeah, this is a midpoint. So a 4th is half a width over from where? Half a width over from 0, 1/4, right? 1/4 is 1/4 over from 0, right? If this would have been 1 1/4, then we'd say, oh, it's a half a width over from 1. If this would have been 2 1/4, that's half a width over from 2. But it's a 4th, which is a 4th over from 0. So that's why this integral started at 0. I have 10 of them times a width of a 1/2. That's a total width of 5. So therefore, this one has to go from 0 to 5. Or I could have plugged a 10 in here. I got 20 minus 1 is 19, 19/4. That's 1/4 away from 20/4. So my right edge must have been at 20/4 or 5. So that's how you can turn this into that. All right. Time is 5, almost 5 after. Oh, 103. There it is. Okay, you guys do that one. You got 5 seconds. Go. 4, 3, 2,
No,
1.
this
Okay.
is too much pressure.
Actually, it doesn't take that. Once you get the hang of it, it doesn't take much longer than that, to be honest with you.
I think
A little longer. Okay, 3 minutes.
that's a significant number.
like I said, when you're writing a sigma, there's just more work to do because you know, to write a sigma, you have to see a pattern. And to see a pattern, you have to write out terms. And so there's not much, there's really no way around doing some of that work. Going back the other way, all the information's there. And so you can kind of think your way through it without having to write much down. All right, so where would we start? Now, I'm sorry. Now, where does the integral start? Where do I start? What do I look at first? I like thinking about the width, the 3/20. And sometimes this 3/20 will be sticking out in front of the sigma. Okay, so the 3/20, I think of that as the width. Down here, that's going to be the dx, right? So the 3/20 is going to be the dx. What about this? What about the function? It's just going to be e to the x. This messy stuff is where the x is. Okay? How do we figure out where to start? Let I be a 1. So we let I be a 1, we get 2 plus 3/20. 2 and 3/20. So that right there tells me what kind of rectangles is this representing? Right. 20 right rectangles is what I'm looking at here. It started at 1. That's another big hint. I see a 20th here and a 20th here. That tells me it's probably not midpoint. It's probably a rectangle. Unless this was 6/20. Sometimes they don't reduce it and it kind of tricks you. If this was 6/20, and then in here I had 3/20, that would actually be a midpoint because 6/20 would reduce to 3/10. And so then it actually is a midpoint. So you got to look out for that. But so you put a 1 in, so 2 and 3/20. So if your width is 3/20, 2 and 3/20 is 1 width over from 2, right? Now, if that 2 hadn't been there, then this would start at 0, right? 3/20 is 3/20 over 1 width over from 0. But 2 and 3/20 is over from 2, so this one's going to start at 2. And then how do we get that last number? Plug in a 20. One way to do it is plug in a 20. 3 times 20 is 60. Over 20 is 3. 3 plus 2 is 5. So this is going to go from 2 to 5. Now, and that's only because they're rights. Since they're right rectangles, your last one actually will be at the right edge. So that's 5. Or you could say the width is 3/20 times 20 rectangles. That's a total width of 3. So if it starts at 2, it's got to go to 5. Okay? All right, try that one. That's messy.
I'm assuming it's gonna get TV.
Oh. Oh. I just noticed something. I just noticed a problem. Yeah.
I was gonna say, how am I supposed to do this?
I accidentally erased it.
Thank you.
Yeah, that's, yeah. After we got done with the other class, I accidentally erased the width. That's pretty important.
I was sitting here like,
That's important.
am I missing
That's an important part. Okay, so the 1 over n is the width, right? So we identify that. So the 1 over n is just going to turn into the dx. And again, we kind of know that because think about the limit part of this. Now, you don't really have to. Somebody in the other class asked this. They said, so when doing this one, the limit really doesn't have anything to do with it. And that's true. Simply in changing this into an integral, you don't have to do anything with this limit part. Nothing. Okay? But it's important, and we're going to talk about it here in a second. But if you think about the limit as n goes to infinity, that's just 0, right? That just goes away, right? But it's not going to equal 0, but it's tending towards 0. But again, that's the idea. The width becomes nothing. And so that turns into the dx. What's the function, do you think? Cube root, or x to the 1/3 if you wanted to do that. Cube root of x is what the function is. This messy stuff in here is where the x would be. If this was all expanded out, it would have been 3 plus something, 3 plus something, 3 plus something. Matter of fact, we should do that next. Let's put a 1 in for I. So we get 2 times 1 is 2, 2 minus 1 is 1, so we get 3 plus 1 over n, 1 over 2n, excuse me. Now what's that mean? Number one, it's a midpoint, isn't it? 2n here, n here, makes me think this was a midpoint. So if my width is 1 over n, what's half of a width? 1 over 2n, right? We said you double the bottom number. That's how you take half of a fraction. So if the width is 1 over n, half a width is 1 over 2n. So this is saying half a width over from 3, which means the integral must have started at 3, right? Because the first midpoint rectangle will be evaluated at 1 midpoint or half a width over from the beginning. So this has to have started at 3. And then how do we tell where it ended? Well, we have 2 ways. One way would be to take the width times how many rectangles? How many rectangles do you have? N. What's 1 over n times n? 1. Total width is 1, so this integral goes from 3 to 4. Or we could have plugged in an n, right? You want to know where it starts? Put a 1 in for I. Want to know where it ends? Put an n in for I. Now the problem is, when you do that, you end up with 3 plus, then you get 2n minus 1 over n. Excuse me, 2n. Now split that apart. 2n over 2n is 1 minus 1 over 2n. Oh, so that's 4 take away 1 over 2n. Well, remember, 1 over 2n is half a width. So 4 take away half a width. That means your last midpoint rectangle would be 1 width back from the right edge, which is 4. 4 minus 1 over 2n. So that tells you the right edge had to be 4. So that's another way. But again, what I will see people do is I'll see people put like 3 1/4 here, 3 over 2n, or 3 plus 1 and 2n, or some weird things in here. Especially when they're midpoints and lefts, right? You got midpoints especially. They don't start at the left or the right edge. They're half a width over from each of those. And so you calculate that. But again, it should be able to get those parts of it. And they're going to be nice whole numbers. I'm not going to give you ones that start at decimals or, you know, even though integrals can do that. We won't get into ones in these problems where that happens. Now, let's, again, one last time. I think you guys got this, but let's talk about this. You know, on this problem where it had ends and had infinity, the only difference is, what does this sigma represent? 20 right rectangles. This was 20 right rectangles. So if I was going to put these two together, I would not put an equal sign between them. This would be an approximate sign. This would be 20 right rectangles, which is an approximation to this area. But on this side, what would I put? This would have an equal sign, because these two things are equal. This is an infinite number of rectangles added up. That's the definition of an integral. An integral, the area under curve, is an infinite number of rectangles added up. So that's the only difference between those two sigmas. This is just a set number of rectangles. This is saying an infinite number of rectangles. All right. So we want to be able to do that in both directions. If we look at the quiz review then, we want to be able to do both those things. Today's homework's mostly going to be this last thing, taking an integral, or taking a sigma, turning it into the integral, like we just did there. One other comment on the homework. This was number 11, I believe. And somebody in the other class asked about this. I thought it was a good question. They were wondering if they were supposed to, on this it said evaluate the sigma, and they felt like they were supposed to do the formulas on this one. But this went from 0 to 9. And the formulas only work if you do what? 1. Now, I'll be pretty clear on the quiz whether I want you to use the summation formulas or I expect you to just expand it out. I think on today's homework, the expectation was you just wrote it out. So they wanted you to put a 0 in, get 1 squared, put a 1 in, get 2 squared, put a 2 in, get 3 squared. Write it out all the way out to the last one. When you put a 9 in, would be 10 squared. And then they wanted you to use your calculator to just add that up. Okay? And that's what I would want you to do. If I was going to have you do it on where you use the formulas, it'd be more like this. Sigma 1 to, it'd be a bigger number. Something where I'd want you to actually use the formula. So here you would want to FOIL this out. You'd want to split it into your different sigmas, like we did on the LH worksheet. We did in, you know, so you'd have sigma I squared, 2 sigma I, sigma 1, then use your summation formulas and go from there. Now this one you actually could rewrite, couldn't you? If you want to make this go 1 to 10, don't you just have to shift it what? To the right one. So this would be the equivalent of k equals 1 to 10, k squared. If you shift it 1 to the right, you minus 1, which you just make it that. Then you could use your formulas real easily. But I think the intention was, and I'll be real clear on that, if I say expand out the sum, I want you to expand it out, and then you'll be, I think I'm going to let you use calculators on the quiz, so that way for any of these sums, even though you're showing you're expanding them out, writing them out, you can then use your calculator to get them. Now also notice on none of these did it say to evaluate the answer for these. Like on these problems back here in 23, you just stopped at the sigma, that's all you had to do. But I might also say evaluate that. Well, when I say evaluate it, I'm probably meaning this right here. Okay? We can do this on our calculator too. So if I tell you to evaluate a sigma and not using your sum formulas, but just to evaluate the sigma, you can just type that in because we have that sigma notation on our calculator. Okay? So say we wanted to compare these 10 midpoints with the exact area. Okay? So I might just have you do that. All right? If the directions say use the fundamental theorem, I want to see antiderivative f of b minus f of a. I want to see that worked out. Okay? I think that's really all probably for today. So, yeah. Okay, so there's your homework. Now, I will tell you that for your own benefit, for practice, 27 through 33 odd, they do something kind of weird there. Okay, on 27 through 33 odd, and excuse me, I'm going to go off of this for just a second. Here's what they do in the book. they give you this sigma and they give you this integral. And they say, explain how this ends up being this. I don't know that I want you on all those problems to write out and explain how you get it. So what we decided in the other class is they were just going to cover this up with their hands.
Be honest.
You know, that's kind of the honor system. You know, cover, I mean, it's kind of like the answers in the back of the book, except they put the answers right on the same page for you, right? So just cover this up with your hand and see if you can get it. Now, several of them come out the same, I think. But again, it's just good practice in turning the sigma into the integral. Okay, then there's a few of them. Then these, they just give you the sigma and you have to come up with the integral yourself. So those for sure will be good practice. But if you want to challenge yourself a little more there, do that. And 46 is kind of a combination story problem, sigma kind of situation. All right, it's not that many problems. They don't take that long. You might be able to get them all done in class, to be honest with you. Melissa, you want to go?
Oh. I was away. If I could. Ice one?
I can get a drink.
Oh, that one? Oh, yeah, you say that. Class. Good luck, Melissa. I believe in you.
I'll meet you.
Where's she going?
She's got a doctor's.
Ah.
Get started on her good way too.
I got the first one right. Not when you're being distracted by all. Usually it's you. I'm pretty sure it's Tom. Me too. Why are you